Okay, hi everyone. So in this example, we are actually given the relation of a boat's velocity versus displacement relation, and it's moving in a straight line. So we notice that there are actually two ranges of its velocity relation, whereby from 0 to 100 meters, it's actually v squared equals to 4s, while from 100 meters to 400 meters, it's actually v equals to 0.2s. So we actually have to analyze these two separate ranges. We are also given some initial conditions whereby at t equals to 0, we actually have the displacement equals to 0. And for range 1, I've actually rewritten the velocity as this to ease my calculations. Okay, so how do we attempt this question? I want everyone to actually work on the basis of using the basic idea of velocity equals to rate of change of displacement, which is ds per dt here, and acceleration is then the rate of change of velocity, or dv per dt. Okay, let's look at the first situation where we know that velocity, which is equals to ds per dt for range 1, is given by the relation of v equals to 2 s to the power half, or square root of s. So in integrals, what we then do is to bring the relevant parameters to its respective sides. So means that I'll actually bring the s parameters to one side and the t parameters, in this case we don't have any, to one side. And I'll then do the integral. Okay, as you know, this actually will integrate to s to the power of half divided by half, while on this side is actually going to be 2t, and it's an indefinite integral plus c. So in order for me to solve this, I actually have to use my initial conditions, whereby, as mentioned earlier, when t equals to 0, s equals to 0, and if you substitute into it, you'll find that c takes on the value of 0. And therefore, I can actually get the relation of s, which is going to be s equals to t to the power of 2. Okay, so we have established the relation of displacement versus time for range 1. Now we want to look at range 2. Similarly to range 1, we actually need some initial conditions for range 2. So we can actually look at this as our initial condition. So here we actually have at s equals to 100. We know from range 1's relation here, t would then be equals to 10 seconds, because it will be square root of s. Okay, and we also know that v will take on the value of 20, but we won't likely use this value. Okay, so now we actually attempt the same on range 2. So ds per dt is equals to 0.2s, and therefore similarly I bring the s parameter to its respective side and the t parameter to its other side, and I do the integral. So if you're familiar with calculus, 1 over s integrated with respect to its s will give me log to the base of s, and this will be equals to 0.2t plus, again I have an indefinite integral, so this will be another constant that I need to find. So we can find this c1 by using the initial conditions mentioned there. So when t equals to 10 seconds, I actually have s equals to 100. So therefore c1 is equals to log to the base of 100 plus, minus, so 0.2 times 10 seconds, this will be 2. So I can rewrite this as log 10 to the power of 2 minus 2. And if you know your logarithms, I can bring out the 2. Log 10 minus, I can treat 1 as log e. And I can rearrange this as log 10 over e squared. Okay, There's a reason why I put it this way, is to simplify my calculations. So therefore, the complete equation for range 2 will be log to the power base of e s 0.2 t plus log 10 e squared. So I can actually get the relation of s in exponential form. So s will be e to the power of this whole term here, 0.2 t plus log 10 over e squared, which I can then separate out, e 0.2 t and also e to the power of log 10 over e squared, which would then give me 10 over e squared e to the power of 0.2 t, and this value here is actually 13.53 e to the power of 0.2 t. Okay, in this question it's also asked that we find the time when it actually reaches the displacement of 400, and we can actually get that from this equation. So when s equals to 400, we equate it to this equation, 13.53 e to the power of 0.2 t, and therefore we can find t is actually equals to 16.93 seconds. Okay, so we are required to roughly draw or sketch the s versus t graph, so let's do it here. So s versus time. So from 0 to 10 seconds, we are going to get a relation where s equals to t squared. So here s equals to t squared, while from 10 seconds to 16.93 seconds, we're going to get it in this form where it's exponential. So s equals to 13.53 e to the power of 0.2 t. So we've established the displacement versus time graph. So now let's look at the second part where it says to establish the acceleration and s graph. So we know that acceleration, as mentioned, is rate of change of velocity. Okay, so I can actually substitute velocity into this equation here. So this becomes, for range 1, is 2s square root, okay, over dt. Okay, so I can bring out the 2 as a factor. So I can actually use substitution rule to solve this. So let's make u equals to 2s to the power of half. So du per ds will actually be s to the power of negative half. So what happens is I have actually bring out the half from here, multiply it with the 2, so that cancels each other, and then I minus this factor on top here with 1. So now we know this relation. We can actually get a equals to du per ds times ds per dt. Effectively, what I'm getting, as you can see here, earlier I've mentioned this part here as u, so 2s to the power of half as u. So if you cancel out this ds that you see here, you actually get back the same form of du per dt, which is d2s to the power of half over dt. So let's substitute it back into this. So we know that du per ds is s to the power of negative half, and we know ds per dt, which is actually velocity. So that is for range 1 is 2s to the power of half. So s to the power of negative half times s to the power of half, it cancels each other out. So what we are left back is 2. So this becomes 2 meters per second per second. Okay, so means that from 0 to 10 seconds is actually going to take on, or 0 to 100 meters is going to take on this value of acceleration. So let's look at range 2. Now we know that range 2 we have v equals to 0.2s, so a is dv per dt, which we actually then substitute, it's actually d 0.2s per dt, okay, which we then get the value of 0.2 ds per dt, so which actually means that it's 0.2 v, and the second range, the relation of v is actually 0.2 s, so therefore it's equals to 0.04 s. So we get a relation here where in this case acceleration takes on a constant value, while in this case the acceleration increases with time. So as you can see here, the relation would be a and s, whereby from 0 to 100 meters it takes on the value of 2, while from 100 to 400 meters it takes on the value starting from 4 and to a final value here. Okay.